Hey, so in this video we're going to be deriving Maxwell's second equation, which is an equation that describes how magnetic fields spread through space. So just like how we described how electric fields spread through space in Maxwell's first equation, we're going to do the same for magnetic fields. So for Maxwell's first equation, we started with a point charge because charges produce electric fields, while magnetic fields are produced by moving charges, like charges in a wire. So let's start with a little piece of wire, like a little cylinder of a wire. We'll call it dl because it's a little piece of wire, a small length of wire with a current I flowing through it. And current has direction, so we might as well give the piece of wire direction as well. So now dl is a vector. So this generates a magnetic field, a small magnetic field because it's a small piece of wire, and we'll call that dB. So say we wanted to work out what the value of dB was at this point over here. So what's the little bit of magnetic field generated by the little bit of wire at this point here? Well, it would be helpful if we could describe the position of this point in relation to the length of wire using a spherical polar coordinate system. So say the point is r away, and let's make a little z-axis that goes straight through the wire. And you have this angle here, theta, and the other angle, phi, which is an angle about the z-axis, would be going either into or out of the screen. So we know that we can work out dB using the Biot-Savart law. So the Biot-Savart law says dB, it's a vector equation, is equal to mu naught, which is a number that tells us how easy it is for a magnetic field to spread through vacuum, times I, divided by 4 pi r squared times dl, the vector cross-producted with r hat, where r hat is a unit vector in the same direction as r, but with length 1. We can simplify the Biot-Savart law to make it suit our case a bit more by introducing some polar coordinates. So the scalar part remains the same, but when we evaluate this vector cross product over here, well, the cross product of two vectors is just the magnitude of the first vector, dl, times the magnitude of the second, which is just 1, times the sine of the angle between them, which in this case is sine theta, because this angle here is the angle between dl and r. And so that's the magnitude of the cross product, but the cross product outputs a vector, and the direction of this vector will actually be phi hat, because it will be directed straight into the page. So in arrow notation, that's how you denote something into the page, and that's the same direction as the angular coordinate phi. So we know what dB is by this vector equation, but it's also worth noting what dB is in spherical polar coordinates. So in spherical polar coordinates, we can write dB as dB r plus dB theta hat plus dB phi hat, where this is the r component of dB, the theta component of dB, and the phi component of dB, using these unit vectors. It's basically the equivalent of ijk in spherical polar coordinates. So now we know what dB is, it might be worth looking into the divergence of dB, because the Maxwell's second equation is to do with the divergence of B as a whole. Well, the divergence of dB can be expressed because it's now in spherical polar coordinates. We can see that it's equal to 1 over r squared times the r derivative of r squared dBr, the r component of B, plus 1 over r sine theta times the partial derivative with respect to theta of b theta sine theta, plus 1 over r sine theta times the partial derivative with respect to, no surprise here, phi. Oh, this is meant to be a dB, of dB phi. Now, this looks really nasty, and this formula I didn't pull out of there. Well, it looks like I pulled it out of thin air, but it's just the formula for the divergence operator in spherical polar coordinates. But if you look at dV and you compare it with the Biot-Savart law, you notice that it only has a component in phi hat. This tells us that dBr and dV theta are both 0. So if this is 0, then this whole derivative vanishes because it's the rate of change of 0, which is 0. Same logic for the second term. Now we're just left with this term here, and this is and we can handle this a bit well too, because if dV is equal to nothing but dB phi, and we differentiate dB now, dB only depends on r and theta. So if we differentiate it with respect to phi, we get 0. So this derivative also goes to 0. So that means the divergence of dV is just equal to 0. So that's great. We know what the divergence of a small part of the field is, but what about the whole magnetic field? Well, what we do know is that the integral of dV, so if we sum up all of the dVs, we'll get B. So i.e. summing up all the little bits of field from every little segment of wire. And so let's try integrating both sides of this relationship we just found. So we'll get the integral of the divergence of B is equal to the integral of 0, which is just 0. Now, the integral of the divergence can be thought of as the divergence of the integral, because the divergence is a linear operator. So if we take the Riemann sum approach to integrals, it's sort of the same idea as how the sum of a bunch of divergences is equal to the divergence of that sum. So we can write this as the divergence of the integral of dV is equal to 0. We know what this is. This is just B. So we now have Maxwell's second equation, which tells us that the divergence of any magnetic field is always 0 at all points in the field.